For this ODE and these homogeneous solutions, determine where the Wronskian guarantees that there's going to be, that these solutions are linearly independent, fundamental set of solutions. Let's go ahead and compute it. So we have Wronskian of x squared, comma, x minus 1 equals the determinant of x squared, x minus 1. Derivative of x squared is 2x. Derivative of x minus 1 is 1. So that's going to be x squared times 1 minus 2x times x minus 1, which equals, let's see here, so I have x squared, I have minus 2x squared plus 2x. Okay, well that ends up equaling negative x squared plus 2x. Which if I factor, it's negative x times x plus 2, it looks like. No, x minus 2. Yeah, that looks right. So this one actually does have some zeros, but they're isolated zeros. So right, if we were to graph this, so we have our, Wronskian, we have x. This thing has zeros at x equals 0 and x equals 2, and the parabola opens upside down. So it's going to look something like, let me try again. It's going to look something like that. But the zeros, it does equal 0 sometimes, but the zeros are isolated, and so these two functions are linearly independent. And right, you can't get x squared by multiplying x minus 1 by a constant, and vice versa. You'd have to multiply it by x and subtract some other stuff. We're not allowed to do that. You can only multiply y1 by a constant to get y2 if they're linearly dependent. These are fundamentally different. So the interval that the Wronskian is guaranteeing linear independence of y1 and y2 is everywhere, negative infinity to infinity.